Welcome to Intelligent Systems, an introduction to applied informatics. In this video, we're going to look into how to evaluate machine learning algorithms and search in general. So, first of all, we have to formulate a need. So, for example, we want to recognize addresses on letters in a postal service. And then we have to assess whether this need has been met by the solution that was provided. The problem with such a general approach is that it's extremely difficult to formulate what actually our need is, and then also it's difficult how to assess and quantify whether that need has been met or not. So instead, what we typically do is something more basic in that we define benchmarks and we have criteria by which to measure and evaluate these benchmarks and the performance on them. But it is very, very important to separate these two things, because the benchmarks are only as good as they fit to some real task that we want to be solving. And often that might not be the case. And you remember we had a discussion, for example, about recognizing the addresses on letters being the real problem to be met by the benchmark data set of the MNIST handwritten digits. Now, you see where the connection is, but whether the MNIST handwritten digits are in any way helpful to solve that real task of recognizing addresses on letters is highly questionable, because the MNIST data set is so standardized, digits in the center, clear black background, one style of handwriting, the 7 written in a kind of US way, not in a German way, and tons of other small things why the MNIST data set would not be representative for handwritten digits in Germany on some letters sent around in Germany. So, very important, there is a difference between real problems in the real world and benchmark data sets that we define. However, it's very difficult to assess the real world problems. We're defining benchmarks and we evaluate these benchmarks. Now, how to do the evaluation? We have to distinguish what is predicted and what is correct. And we can build a matrix of all of these combinations: correct, not correct, predicted, not predicted. So we have 4 possibilities, and it breaks down as follows. If we have this as total data, these are the true negatives. They were not predicted and they're not correct, as opposed to the correct ones here, and when they're overlapping with the predicted, these are true positives. Now we have here the false positives, so those were predicted, but they were not correct. And we have the false negatives, they were correct, but they were not predicted. 4 possibilities, TP, FP, FN, TN. How can we maybe aggregate them to express something that is a little bit easier to understand? Let's make a concrete example. Think back of our recognizer of location and sentences like Don Denver will be playing in Denver. John and Paris went to Washington, and Denver is a city in Colorado. The underlined 4 items here are locations, and our predictor, our machine learning algorithm, predicted these 3 over here. Now let's see how that translates into these measures of TP, FP, and FN, and then how to turn that into some higher order variables of precision and recall. Denver and Denver over here and over here is correct, so that means we have 2 true positives. But we have a false positive. We thought, or our algorithms thought, Paris is a city, when in fact the correct thing was that Paris was a name. So we have 1 false positive. And our algorithm did not know about Washington and Colorado as locations, so it has 2 false negatives. We aggregate true positive, false positive, and false negatives into precision and recall. Precision is how many predicted items are correct, and recall is how many correct items are predicted. Let's look at this again in terms of the Venn diagram over here. So the true positives are where correct and predicted intersect, over here. And in precision, we relate that to everything that we predicted. And in recall, we're related to everything that was correct. So TP plus FN and TP plus FP over here. Now let's apply this to the example that we had. So TP was 2, so in both cases we have 2 over here, and then we divide for the precision by TP plus FP, so 3, and for the recall by TP plus FN, that's 4, so we get 2/4. Now typically, when the precision is high, that means that the recall is low and vice versa. Somehow both measures go against each other. And therefore both measures are needed. We cannot just do with one of them. And that's the reason why there's also a way how to integrate those measures and come up with one final measure, the F-score, as the harmonic mean of precision and recall. And harmonic means it's 2 times precision times recall divided by precision plus recall. So if we put on our numbers as we calculate them, we get 0.57. So this was roughly 0.66, this was 0.5, so 0.57. Now let's assume we wanted to manipulate the precision or the recall, and then to motivate why we need that F-score, because that cannot be manipulated. So we're increasing the precision artificially by only predicting very few items. So by predicting only very few items, we make very few mistakes, and that means the precision goes up. But of course, if we predict only very little, then the recall will go down. On the other hand, if we want to increase the recall, we just predict everything that is in the database. The recall will be very high, but at the same time, we will not be very precise, so precision will go down. So because of these possibilities of manipulating P and R, we have the S-score, because as you increase one, the other one will decrease, and that means the F-score will decrease. Let's see concretely how this could happen. Now imagine the following situation where we have a huge imbalance, that our database is full of items that are not predicted and are not correct, 1 million items. We do have 60 items that are predicted, so 20 of those are correct, but 40 are incorrect. And overall, we have in this huge database only 80 correct items. Now let's calculate precision and recall. So that's 20 out of 60, so 20 true positives out of 20 plus 40 predicted ones. So that's 1/3. And recall is 20 by 80. We have 20 plus 60 correct items, and 20 true positives by these 80 is 1/4, so 0.25. And the F-score will be 0.29. Now let's say somebody wanted to manipulate these results, and they would just care that they get the precision very high. So what do they do to make the precision very high? Instead of predicting the 20 items as before, they make this much more rigorous and predict only the one item that they're really sure about, and not 60. And the one item that they were so sure about is indeed correct, so we have one true positive. And we're dividing that by the predicted one, which was 1. That means bingo, precision is to 100%. We cannot do any better than this algorithm. However, look at what we've done to the recall. So the recall is now 1 true positive divided by 80 positives that were overall in the database, so 60 plus 19 plus 1, and voila, the recall is down by an order of magnitude to 0.0125. And that means that also the F-score is down to 0.025. Before, these were 2 orders or each one order of magnitude better. So while we increased precision, we decreased recall and we decreased F-score. Now let's do the opposite and try to decrease and try to increase the recall. And now we're predicting everything that is in the database. So the database has overall 1,120 items. And as we're predicting everything, turns out the vast majority of our predictions is poor. So 1,040 wrong predictions, but 80 correct ones. And since we're predicting everything, these two entries are 0. The precision is now 80 divided by 1,040, so that means it's more or less 0. But the recall is 80 out of 80, so we're at 1. The F-score, on the other hand, the dominating factor will be the precision, so this goes down to 0. So again, we increased the recall, but the F-score and the precision went down to 0. Now this is quite interesting. So you cannot really trade off, or you cannot really achieve good recall and precision, or not. It's very, very difficult. That's an interesting question because this is a problem to Google as well when it's presenting to us its search results. So does Google have a high precision or high recall, or did Google actually achieve to get high precision and recall? And that is really, really an interesting thing to think about. So when you look at the first results, which we typically do, the first page of Google, then it has very high precision. Because for many, many queries, we will find a good result somewhere on the first page, and that means precision here is very high. But in fact, we have no idea what the precision of the remaining results is. Google is telling us, for example, for this very specialized query, that there are 76,000 results. We will not look at anywhere close to all of these. And if you type in a bit more general query, you will get millions of results that Google is telling you about. But none of us has ever seen these results. They're simply not visible. We have to trust that these results are meaningful. So the recall may be high as indicated by that high number. And that is the reason why Google is reporting us. Why is Google giving us this number? Did any of you ever use this number for something? No, we typically don't. However, the reason why Google is doing this is to suggest that it's high recall, that it's very comprehensive, and that it has a lot in store. And but of course, we cannot really test it. So Google is focusing on the precision of the first page, and it tries to convince us that recall is also high, but in general, we do not have a way to test this. And with some other search engine, I once really bothered, and I clicked through the first 100 pages. So that means I got to search result 1000, and believe me, the results at position 1000 were really, really poor. And you can imagine how poor things get as you're hitting the 1 million, the 1 millionth items. So in that sense, Google is really a funny beast in that its precision on the first page is really high. The recall we cannot really assess, but by us telling us about the total amount of search results it found, it's kind of leading us to think that recall is also high. Another aspect in precision and recall is that searches can be, and then machine learning tasks can be very, very different in nature of what we want. It's not always that the best F-score is really what we want, and that we want precision and recall in combination to be as high as is possible. There are some tasks where precision matters more, and there are other tasks that recall matter more. So think of our Google example. In web search, precision is more important. So time matters. There's actually tolerance to overlooking. It doesn't really matter. Typically, the kind of things we're searching online, they're redundant, and that means if something gets missed, if there was another page that was also relevant, but Google brought it only on that result only on page 50 or so, that doesn't really matter that much. So we're tolerant to overlooking by Google, and there's plenty of redundancy because for most things we're looking for, there are multiple pages that could be relevant. And that means that precision is really what we're after because of the time. We don't want to spend much time, and we're just looking at the first page and then continue searching. Patent search, on the other hand, is different. In patent search, time doesn't really matter, but we have to be accurate. If the patent lawyer is overlooking anything, and then we start the patent process in which we're saying this is unique and nobody has ever looked at it, and turns out later that something was overlooked, then that's a huge problem in the process. So time does not matter. We're absolutely not tolerant to overlooking any evidence, and it's also unlikely that there's any redundancy. The very nature of a patent means that it's unique. It covers one specific item that nobody else is allowed to copy. That means there is no redundancy in a patent database in contrast to the databases of all web pages. So in a patent search, the recall would be very important, and we'd rather spend the time to take the full precision and go through the results hand by hand, one by one. And you can imagine that in a medical setting, there's also often a balance between recall and precision when we're diagnosing a cancer. And if we have a very high precision, then it's great because we can inform only the patients which are extremely likely to have a problem. And that's very good because we're not causing any harm to all of the others. But at the same time, we're missing patients who may benefit from an early treatment because we didn't inform them. So we could create another diagnostic kit where we are more lenient and we put up the recall high. But that means we're informing maybe many patients who actually do not suffer from the disease that they may suffer from the disease, causing a lot of psychological problems when they have to deal with that situation of uncertainty until it's finally resolved. So typically in a medical setting, what you want is high precision. There are other measures how to evaluate machine learning algorithms and search in general, and these are, for example, plots where we plot the recall against the precision, and you see how an increase in one leads to a decrease to the other ones, or receiver operating curves, which typically look like this. You plot on the one axis the false positive rate, on the other axis the true positive rate, and the true positive rate is the true positives by all of the relevant ones, and the false positive rate are the false positives by all of the ones that are not relevant. And a third measure is the accuracy. These are the true positives and true negatives divided by all of the items that we had. Now, accuracy is a nice measure, but we have to be very, very careful with accuracy when we have a huge imbalance between our categories. So imagine, for example, the spam and ham dataset, in which I think 13% were spam and 87% were ham. They were good messages. Now, if we report the accuracy, that means we're considering really all of the messages, and things will be dominated by the true negatives by the correctly predicted ham messages. And that means we could just predict that everything is ham, so everything is a good message, no spam in our data set, and we will be already at 87% that we get correct. So when the two groups are imbalanced, then accuracy can be very misleading because our baseline random estimation is not 50% anymore, but it's the size of the larger group. So besides precision and recall and the aggregation of the F-score, there are other dimensions to how to evaluate data, and one important aspect is cross-validation, in which we have data given and we basically divide it into k different groups, and we train our algorithm on k-1 groups, and we leave the final group for the prediction. And then we iterate this process and do this over and over again, and that gives us a more robust overall estimation of how good or bad our algorithm is. Then in earlier videos we spoke already about bootstrapping, and that applies here as well, and that is very simply how robust is our prediction. When we make small changes in the data, we want small changes in the prediction. And that is important because we cannot exclude that there are small errors in our data. So also for machine learning predictions, we want to have this property. And finally, a huge problem in machine learning is so-called data leakage. How do we ensure that the training and test data are really different? And it's no surprise that we are good on the test data if the test data may not be identically present in the training data, but there are variants of the test data in the training data that are so close that we're essentially possibly learning by heart what is in the training data. So the question is, how similar can the test data be to the training data? And detecting data leakage is a very, very difficult problem because you have to set off the trade-off between what is dissimilar enough that you have them separated, what is similar enough. So you need good sampling strategies in order to have a balanced and even way how to sample your test data from your overall data. And then finally, as I said in the beginning, we are working on benchmarks, and benchmarks are only a surrogate for the real problems that we're trying to solve. And that is something that we must be very aware of, because the benchmark might sometimes be very far off from the real problem to be solved. So we should always pay attention to how the benchmark was defined and what problems that might entail, what size the benchmark has, which characteristics, is it adequate for the real task, and in which way might the benchmark be biased. So think back of the ImageNet benchmark and competition. The original ImageNet dataset was put together by running web searches for images and automatically collecting these images and then assessing them later on by hand. But this very process of how it was obtained is, of course, influencing what is present in those images, because only material that is online available. And we know that online photographs are not really representative of the world as a whole. There are far many more cat photos than, let's say, insect photos, when in reality, in the real world, there are more insects than cats. But for some reason, we love to photograph cats more than we love to photograph insects, at least the majority of us. And that means any of these benchmark data sets does have somehow bias in it, it has its characteristics, and it's not meaning to say that we're not allowed to use benchmarks, but we should be aware of these characteristics. So benchmarks are really good, and the competitions such as CASP for structure prediction, ImageNet for image classification, or competitions in biomedical question answering, these are all fantastic, and they are based on benchmarks, and they paved really the way for great scientific discoveries that were made through them. So take-home message for today: you should know what precision and recall is and why they work against each other, how they can be aggregated in the F-score, and you should be familiar with the concept of cross-validation, bootstrapping, and the role of benchmarks.